So in this video, I'm going to introduce you to non-deterministic finite state machines. You'll need to remember what a deterministic finite state machine is, particularly its formal definition in quintuple form, what relations on sets and functions on sets are, and have a basic idea of the difference between determinism and non-determinism as concepts. If you're not really sure about that, look at your textbook page 41. You should also understand what a dead state is. Ultimately, the difference between a deterministic and a non-deterministic finite state machine comes down to delta. So for the deterministic variance, which you've already seen before, you know that delta takes the form of a transition function. Whereas for the non-deterministic finite state machines, this is relaxed to be a transition relation, and we usually represent it with an uppercase delta instead. What this means simply is that for a deterministic finite state machine, there must be one entry in delta for every state symbol pair, and only one entry. So that means for any given state, there must be a transition out of it for an element of sigma, and there must be only one such transition. Whereas for a non-deterministic finite state machine, we may have no entries, so we can have states without transitions coming out of them for every element of sigma, or we may even have multiple entries, and this is usually what we see as the key difference. So we may have a state with two transitions coming out for the symbol A. So just to make it a little bit more clear, in the state transition diagram, for a deterministic finite state machine, we needed to have a transition coming out of Q0 for every element in sigma, and there could be only one. But now when we extend this to the non-deterministic variance, we may have multiple transitions coming out of Q0 for the same element. And we may also contain transitions into other states that are labelled with epsilon, and we call these epsilon transitions. What happens is that this allows the machine to transition from one state to another without consuming any input. The formal definition for a non-deterministic finite state machine is very similar to that of the deterministic. So it is still just a quintuple, i.e. a tuple with 5 elements, and K still represents the set of all states, sigma still represents the set of symbols that the input strings can be taken from, S still represents a single start state for the machine, and A still represents a set of states which are considered to be accepting states. The only difference is delta. And here, delta is allowed to be a transition relation and can be any finite subset of this Cartesian product. So to simplify it, it is simply take a state and an element of sigma or epsilon, and you have the state that we can transition into. So for this first transition, the element of this would read Q0 upon A, and we transition into Q1. And for this one, would read very similarly, Q0 and on epsilon, transition into Q3. So for accepting, the rule for a non-deterministic finite state machine is simple. If one of the paths through it results in an accepting configuration, then the finite state machine accepts. So that is, if there is a way through the NDFSM to an accepting state, where the machine arrives in that accepting state with no more input symbols in the input, then the machine accepts. You might like to pause the video here for a second and see if you can determine if any of the strings on the right are accepted or rejected by the machine. Okay, so the strings outlined in green are accepted by the machine. So for instance, AB here has a path where we can travel through Q2 and then Q4, and then we will arrive in Q4, which is an accepting state, and we will have consumed all of the input stream. So that is accepting. The same can be seen for AA through this path, and B by taking the epsilon transition here, which doesn't consume any input, and then consuming the lone B on the tape with the transition into Q4. You can see that, for example, for this state here, there is no path through the machine that ends up in Q4 with an empty string. The only paths possible take us into Q1, where we will have an empty string and therefore halt in a non-accepting state. The same is true for going through to Q2, and even if we go through via the epsilon transition down to Q3, we won't have any transitions out of Q3 that will consume the A. You can see the similar sort of reasoning for the remaining strings, and in particular, the empty string is not accepted at all. So that's it for this introduction to non-deterministic finite state machines. So what you should know from the video is the basic difference between the deterministic and non-deterministic versions in terms of how their graphical models might differ and how their formal definitions differ. And you should have a rough understanding of how a non-deterministic finite state machine operates and under what conditions it accepts or rejects strings from a language. If you want more information on this before the lecture, you can see page 66 onwards in your textbook.